Okay, in this lecture we're going to start the section 1.6 material on applications of linear systems. And in this section we're going to discuss some simple applications that involve solving systems of linear equations, which is what we've been doing in the first part of this chapter 1 material. So in our first example, we are asked to find a quadratic polynomial p of x such that p of 1 is equal to 4, p of 2 is equal to 3, and p of 3 is equal to 4. So that is, we want the equation for a polynomial whose graph would be some, a quadratic polynomial whose graph would be some parabola. And we want that parabola to pass through the points 1, 4, 2, 3, and 3, 4 in the xy plane. Now, in general, a quadratic polynomial will have the form p of x is equal to some constant, let's call it a, plus some other constant, b, times x to the first power, plus another constant c times x squared. And for a quadratic polynomial, we only go up through the second, or the square of x. So we know that we need this polynomial to satisfy three conditions. There's 3 points we're told this graph has to pass through. The first of which was the point 1, 4. That is, if we plug in 1 for x, let's see what we have. We have a plus b plus c, which we're told has to equal to 4. We're told that p of 2 has to equal 3. So let's see what we get when we plug in 2. We have a plus 2b plus c times 2 squared would be 4c, which has to equal 3. And p of 3 has to be 4. So plugging in 3 for x, we have a plus 3b plus 9c is equal to 4. So what we have here is a system of 3 linear equations in 3 unknowns. So let's see what we have here, if we can solve this system. So in order to solve this, we could express this as an augmented matrix. And we would have, for our first equation, the coefficients of a, b, and c are 1, 1, and 1. And we have the sum of a plus b plus c has to equal 4. For our second equation, we have 1a plus 2b plus 4c has to equal 3. And for our third equation, we have 1a plus 3b plus 9c has to be 4. So we want to solve this system by performing row reduction on this matrix to put it in either row-echelon or reduced row-echelon form. So starting with our first row, we have a lead entry of 1, and we're going to use that pivot to kill off the 1 entries in the lead coefficients of our second and third rows. So for our first operation, I'm going to take row 2 and subtract row 1 from it. So my first row will remain as 1, 1, 1, 4. My second row becomes 0, 1, 3, negative 1. And in this same step, I'm going to take row 3. I could take either minus row 2 or minus row 1. I'll stick with row 1 here. So this would give me 0, 2, 8, and 0. All right. So now, simplifying a bit further, well, I have the 1 as the leading coefficient in my first row with zeros above and below it. I have now a 1 for the leading coefficient in my second row, and I need to eliminate the 1 that appears above that and the 2 that appears below it. So to eliminate the 1 that appears in the first row above that lead entry, we could take row 1 minus row 2, which would leave me a first row of 1, 0, -2, and positive 5. My second row will remain as 0, 1, 3, -1. And to simplify the 2 as the lead entry in my third row, I could take row 3 minus 2 times row 2, which would leave me 0, -2 plus 2 is 0, minus 6 plus 8 is 2, and then 2 plus 0 gives me 2 here. So in my last column, or my last row, I want this leading entry of 2 to be 1. So an easy way to transform that to a 1 here is to divide my third row through by 2, or equivalently take half of my third row, which would make my third row 0, 0, 1, 1. Now in this same step, if I'm thinking about moving towards reduced row echelon form, I know that I want this top right entry of -2 to be 0. So in this step, I could use my last row, which has a leading entry of +2, to kill off that term by taking row 1 plus row 3, which would make my first row 1, 0, 0, 7. And for now, I'm going to leave my second row alone. So in our last step, we just need to eliminate this factor of 3 in the second row, third column. So I can use my third row to do that by taking row 2 minus 3 times row 3, which would give me 1, 0, 0, 7, 0, 1, 0, and -4, and 0, 0, 1, 1. So we have then, from my first equation, A is equal to 7. From the second equation, or second row, B is -4. And from our third row, or third equation, C is equal to 1. So writing out the polynomial that we were interested in, P of x is equal to A, which was 7, plus B times x, so here we have minus 4x, plus C times x squared, so plus 1x squared. So this would be the polynomial, quadratic polynomial, that passes through the indicated points. And we can check our answers here if we have our resulting polynomial. Well, we can substitute 1, 2, or 3 in for the values of x, and double check that we do indeed get 4, 3, or 4 as our output.